We present MobileH2R, learning generalizable human-to-mobile robot handover exclusively from scalable and diverse synthetic data. In this work, we focus on a human-robot interaction task, human-to-mobile robot handover. Our goal is to enable mobile robots with a mobile base to reliably receive moving objects of various shapes from humans in large workspaces using egocentric observations. Compared to traditional fixed-base handover, this task requires more perception, capturing whole-body human motions, and controlling higher degrees of freedom, making it a challenging problem. This task faces two main challenges: scaling human-to-robot handover training and managing mobility complexities. Real-world training is costly and risky, while simulations struggle to generate diverse assets with realistic human motion dynamics and sufficient robot demonstrations. Mobility further amplifies the challenge, requiring coordinated base arm actions and the creation of imitation-friendly and safe demonstrations in larger workspaces. In this work, we aim to enable generalizable human-to-mobile robot handover by addressing these challenges. Our key insight is that generalizable handover skills can be learned entirely in simulation by leveraging high-quality synthetic data without real-world demonstrations. This data includes human motion assets, object assets, and robot demonstrations. To achieve this, we propose a scalable solution that expands both assets and demonstrations, facilitating effective closed-loop visuomotor policy learning through imitation. To scale synthetic and diverse full-body human motion data, we introduce an automatic pipeline that prioritizes both diversity and fidelity. Existing datasets lack task-specific specialization and interactive behaviors necessary for complex human-robot interaction tasks like handover. To address this, we propose a two-stage pipeline. In the pre-handover phase, we use generic motion synthesis algorithms and synthetic digital asset libraries to generate realistic full-body movements. For the handover phase, a task-specific synthesis method creates diverse hand and arm motions tailored to handover dynamics. Additionally, our reactive design ensures seamless phase transitions. The human stays in the pre-handover phase, performing full-body motions, until the robot comes within range or the pre-handover time limit is reached. We have automatically generate over 100K interactive handover scenes, featuring diverse human and hand motions. To ensure safe interactions, we adopt imitation learning over reinforcement learning. We leverage motion planning for safe and imitable demonstration generation. For safety, we optimize the planner by loss to avoid collisions with the human body and prevent the robot from entering the human's blind side. To ensure imitation-friendly learning, we focus on making the vision-to-action mapping learnable. While the demonstration generator maps oracle states to actions without considering vision, our key insight is that effective vision-based state recovery enhances the vision-action association. Leveraging our scalable assets, we automatically generate safe and imitation-friendly demonstrations. Finally, to distill these demonstrations into a visuomotor policy, we employ a 4D imitation learning approach that incorporates both human and object vision inputs, for coordinated base arm action outputs. Unlike previous works that focus solely on hand and object, our approach also includes the human body as input. To address scale differences between body and object point clouds, we apply set abstraction layers with varied sampling radii. The resulting features are merged into a global representation and decoded to coordinated base arm movements, which are essential for controlling a mobile robot. We demonstrate the generality and scalability of our framework through comprehensive experiments. Our model significantly outperforms the state-of-the-art method, Gen.H2R. The results highlight the importance of human involvement and mobility. Unlike fixed-based handover approaches, our method is not a simple extension but instead incorporates human motion modeling and coordinated actions in an end-to-end manner. We also evaluate different data scaling. In demonstration scaling, we find that more demonstrations significantly improve performance, which can improve grasping poses and arm-base coordination. In terms of assets, training on unscalable mocap data harms performance, while more diverse simulation data improves more. Complex demonstrations teach the policy harder-to-learn knowledge, such as avoiding humans instead of colliding. We evaluate various demonstration strategies. In terms of safety, our simple design significantly reduces human collisions. Future obstacle avoidance makes the policy consciously plans to avoid humans, and final pose constraints ensures face-to-face handovers to avoid blind spots. For imitation-friendly learning, we find that encouraging vision-to-action mapping is crucial, enabling the policy to better capture and follow object-human dynamics. It makes the policy to better identify a visible angle and adjust the robot correspondingly. We also deploy our model in real robot Galbot 1+. We use 2 cameras to capture point clouds and segment it use SAM. Our robot has 9 degrees of freedom. We tested our model in various scenarios, demonstrating strong generalization. For example, in healthcare settings, it can accept items from a person lying in bed. In a home environment, it interacts steadily with the person on stairs. These demonstrate that our strategy generalizes well to handover scenarios with varying heights and object geometries. In addition, in a supermarket, the robot smoothly receives objects from a human hand while avoiding both people and shelves. In an office, it safely grasps objects from someone across a desk. These demonstrate that our strategy generalizes well to obstacle-rich environments with various human motion. Our method is more robust than the baseline in real-world deployment. For example, our policy can adjust the robot pose by while when the object's height changes, while the baseline cannot make a proper pose to reach the object. In an adversarial setting, our policy continuously generates coordinated base arm actions as the person steps back, whereas the baseline struggles with coordination. This demonstrates that our policy better generalizes to human dynamics with effective coordinated control. In conclusion, to learn generalizable human-to-mobile robot handover, we propose a scalable pipeline for generating human motion, an automatic pipeline for generating demonstrations, and a 4D imitation learning method. Finally, we successfully make Sim2 real transfer.